3 minutes.
Securing LO2 topping.
Atlas tanks to flight pressure.
250. FTS internal.
T-minus 2 minutes, 30 seconds and counting. Once the rocket lifts off, it will only take about 78 seconds to reach Mach 1, or the speed of sound.
$159.
Vehicle internal.
$155.
Launch sequencer start.
$150.
Securing Centaur LH2.
Securing Centaur LO2.
$140.
FCS launch enable.
FTS armed.
T-minus 1 minute, 30 seconds and counting. The launch vehicle payload, vehicle, and ground systems and Eastern Range are a go for launch.
120.
OCUs armed. FCS count started.
110.
Vent valves locked.
60 seconds.
T-minus
Rocket.
1 minute.
$40.
Stable at step 3.
T-minus 30 seconds.
25.
Status check.
Go Atlas.
Go Centaur. Go GPS.
20. 15. 10.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. RD-180 ignition. And we have liftoff of the United Launch Alliance AtlasV rocket carrying the 12th GPSIIF satellite for the United States Air Force. The Global Positioning System provides worldwide positioning, navigation, and timing service for military and civilian users.
Control.
You are hearing the voice of Marty Milanowski, here providing launch vehicle ascent data.
Speeds and injector pressures continue to look good. RD-180 continues to perform well. And the roll program is now complete. Body rates look good. Engine performance continues to look good as well. Coming up on Mach 1 momentarily. Mach 1. Body rates continue to look very good. Engine performance is steady. Max Q, booster has throttled back as expected. Engine signatures look good. Body rates continue to control right down the middle. Current altitude is 13 miles, downrange distance 8.5 miles. Current velocity is 2,200 miles per hour. Booster performance continues to look very good. Body rates are smooth. Coming up on our closed loop steering segment. And closed loop steering has been enabled. Also a minor roll. RD-180 pump speeds and injector pressures continue to look good. Our CS pyro valve has been fired. System's now pressurizing to flight levels. Signatures look good. Booster performance continues to look very good at this point. Pitch yaw and roll, controlling right down the middle. We've ended the Q alpha limited steering and throttled back as expected. Engine signatures look good. Coming up on our 5G throttle segment. And we have begun throttling to maintain 5Gs. Boost phase chill down is underway. Signatures look good. Pump temperatures are as expected. And we've begun throttling to 4.6 Gs in preparation for BECO. Boost phase cool down is complete. And we have BECO. Engine shutdown looks good. And we have stage separation. Looks like a clean SEP. We have LOX and fuel pre-start on the RL-10. GN2 purge firing is underway. We have RL-10 ignition and full thrust. Coming up on payload fairing jettison, and we do have indication of a good payload fairing jettison. All signatures look good at this point.
This is Atlas Mission Control at T plus 4 minutes 40 seconds. We've just heard Marty Milanowski report the successful execution of the events comprising the early part of today's mission, and all systems to continue to operate nominally. The mission is currently in the first of 2 Centaur engine burns. Our next event, Centaur main engine cutoff, will occur in approximately 12 minutes. I'm now joined by the Air Force's Lieutenant Jason Fischbach from the Global Positioning Systems Directorate. Lieutenant, thanks for joining me today.
Thank you for having me. It's an honor.
Great. Can you tell me just a little bit about yourself?
Okay, as you said, I'm Jason Fischbach. I'm from the Republic of Panama. I come from a family of enlisted veterans. I'm married. I have 2 wonderful sons. When I was growing up and we didn't have enough money for college, it became an easy decision to join the Air Force. So I joined the Air Force about 18 years ago, and after balancing school and work for about 15 years, I finally earned my bachelor's degree in electrical engineering. Shortly after that, I became the first person in my family to become a commissioned officer, and I've been working with the GPS Directorate ever since. I started off 3 years ago with the GPS Directorate. The first 2 years I worked as government lead for the GPSIIF production line, and that was an awesome opportunity. I saw everything from every stage of build and test of the GPSIIF satellites. Then I went on to what I'm currently working, which is the next generation command and control system.
Great. Well, congratulations on all you've accomplished so far. That's quite a feat.
Thank you so much. I really appreciate it.
Since you're very knowledgeable about the GPS program, can you kind of give us a current status on the GPS constellation?
Of course. The GPS constellation remains stable, healthy, and robust. With 30 operational satellites on orbit, the constellation is comprised of 19 GPS-2R and 2RM satellites and 11 GPS-2F satellites. The GPS-2R and 2RM satellites, also known as the GPS legacy satellites, have exceeded their life expectancy. In fact, 18 of the 19 that are on orbit today have exceeded the 7.5 7.5 year design life. Regardless of that feat, they continue to provide reliable position, navigation, and timing services.
That's great. You know, I'm really glad because of the lifetime of the satellites is kind of ending here. I'm glad we're helping you launch a new one today.
Yes, the GPSIIF satellites are
Yes.
vital to the modernization of the constellation, and in order for us to maintain the level of reliability and precision that GPS delivers to users worldwide each and every day.
Can you tell me about some of the capabilities that the 2F satellites bring to the GPS constellation technically?
Of course. The 12 Boeing-built GPS-2F satellites have improved signals, which will enhance the precision of the global position navigation and timing services provided both to support both the warfighter and the growing civilian needs of our global economy. The GPS-2RM was the satellite that directly preceded the GPS-2F satellites, and it introduced the L1 signal, one new L1 signal, and it introduced two new L2 signals. The GPS-2F satellites introduced one new L5 signal. So L1, L2, L5, what all that means is it's just basically a portion of the frequency spectrum. The L1 signal carries probably the most commonly known signal, the L1 course acquisition code, and that's the most commonly known because that's what you're going to have on your GPS watch, your GPS navigation system in your car and stuff like that. The L1 also carries a code called precision code, PY code, and that's for military applications, and it also carries L1M code. The L2 frequency carries L2C, which is a modernized civil signal. We'll talk about why that's important here in a sec. The L2PY, precision code for military applications, and L2M for military applications as well.
Great.
The L5 signal, which is brought by this GPS-2F, is safety of life. It's going to be used for safety of life applications, including aviation applications. The great thing about the GPS-2F satellite is that it has all those signals on board in the navigation payload. And those signals carry information like the GPS date and time, satellite ephemeris, satellite state of health, and ephemeris is basically the location of that satellite. And it also includes almanac information, which is all that other information for the rest of the satellites in the constellation.
Great. Powerful satellites.
Yes. One last thing I wanted to mention was that modernized signal, what that has, that enables this thing called ionospheric correction, which will greatly improve accuracy to all the users.
Amazing. So we've talked about a lot about what we've done in the past with GPS. Can you tell us a little bit of what's in store in the future for the GPS program?
Yes, the GPS program has a lot of modernization efforts currently underway across the space, ground, and user segments. Those modernization efforts include improved or stronger signals. It includes additional civil signals. It includes improved robustness of the overall system architecture, and it includes advanced user or advanced receiver techniques for the GPS military user equipment.
Great. So in terms of your satellites, what's next for GPS?
Okay, so we just, as you see, we just launched the last GPS-2F. We're going to be the next satellite that's currently in development is known as the GPS-3 satellite. Its first satellite, SV1, has just completed baseline thermal vacuum testing, or TVAC. As you know, TVAC is one of the most comprehensive, perceptive, and critical tests that we have in use today. It's where we take the satellite, we subject it to space-like environment, so a simulated space environment.
Test like you fly.
Exactly. And then we review how the subsystem performs. So this gives us insight on how the satellite will actually perform once it's in orbit.
That's great. So can you tell me a little bit about what capabilities that GPS-3 will bring to the GPS constellation?
Yes, GPS-3 is going to bring stronger signals, which will improve our resistance against jamming and spoofing. And jamming is basically, think of you have a radio station that you like, 88.1 megahertz, let's say, and there's a transmitter over here that's broadcasting more powerful signal on that same frequency. Well, you're not going to get what you're expecting. You're going to get whatever that other transmitter that's boosting at a higher power. So this greater power improves our resistance to jamming and spoofing. Another thing that this GPS-3 satellite brings is it brings additional civil signal, the L1C. It's the fourth civil signal. The cool thing about this civil signal is that it's internationally interoperable. And what that means, it will be able to communicate with Europe's navigation satellite, Galileo. I think there's plans in the future for other satellite constellations to do, the navigation constellations to do the same thing. The last thing I think I would say is that GPS-3 boasts a 15-year design life, and that design life would noticeably increase the longevity of the GPS constellation. So the first satellite, SV1, is projected to be available for launch in August of 2016. That available for launch date, it doesn't say that's when we're gonna launch the satellite. It just says this is when the satellite's completed its build and test phase. The actual launch date will be based off a couple of factors, one of them being the availability of a launch vehicle to take us to orbit. The other is operational priorities, and the last thing I would say is the availability of a ground system, a control system that will be able to harness the capabilities these new satellites bring to bear.
Great. Sounds like quite a powerful new satellite.
Yes.
So thank you so much for joining me today. I know that I really enjoyed learning more about the satellite and what we're launching today, and I know I'd be lost without GPS, so thanks for joining me.
Me too. Thanks for having me. Thank you.
No problem.
Appreciate it.
In just a few moments, I'll speak with Boeing's Dan Hart, but before that, let's take a look at a video.
The Global Positioning System is a marvel of the modern age. It consists of more than 30 GPS satellites circling the globe over 12,000 miles above us. In tightly controlled orbits, these U.S. Air Force satellites continuously transmit their signals to Earth. An extraordinary technology, GPS enables anyone with a GPS receiver to determine their precise location and the exact time anywhere in the world, usually within a meter and within a billionth of a second.
GPS is ubiquitous. It's everywhere. It's in our cars, it's in devices that you use to determine how far you've run or ridden your bicycle.
With billions of users and countless devices, it is easy to take GPS for granted. But it is the essential platform for innovations which enables us to do everyday things like buying gas at the pump and getting directions. And amazing things like tracking ice melts and saving lives in ways that were formerly impossible.
The beauty of the GPS system is that it's available for everyone. The cost of entry for any user is simply the cost of their receiver.
Boeing helped make GPS possible. It's been the U.S. Air Force's prime contractor on 4 major programs, replacing the initial group of satellites as their service lives were completed. Overall, Boeing has produced 2/3 of all GPS satellites, more than 40 in all.
Satellites are normally built in a low volume, perhaps 2 or 3 at most. And they're usually sit in one spot, and resources are brought to the satellite.
Now, to ensure that GPS is available whenever it's needed, Boeing has changed how satellites are made. It's producing 12 new GPS satellites using a streamlined process based on its efficient and advanced airplane assembly line techniques.
Our goal is to have the highest quality.
These new satellites bring next-generation performance to the GPS constellation we all use every day. As a result, they are delivering new levels of accuracy to what is already a remarkably accurate system, and they are being built in a much more efficient way, ensuring that this essential technology is available when we need it.
This is Atlas Mission Control at T plus 15 minutes and 30 seconds into the GPSIIF12 mission, and all systems continue to operate as expected. The Atlas Centaur second stage and GPS satellite are currently located over the North Atlantic Ocean, southeast of Greenland. Our next event, the first Centaur main engine cutoff, or MECO 1, is scheduled to take place in about 2 minutes. Here's Marty Milanowski.
PU's controlling down the middle. Body rates are steady. 1 minute to MECO. All Centaur systems continue to look very good at this point in the burn. Approximately 20 seconds to MECO. And we have MECO. Engine shutdown looks good. We have RCS 4S settling. Fuel tank is being vented.
This is Atlas Mission Control at T plus 17 minutes 30 seconds. Marty Malinowski just confirmed MECO 1, or cutoff of the Centaur RL-10C engine. The mission has now entered an extended coast phase, which will last approximately 3 hours. Following MECO 1, the mission trajectory changes from a southeasterly heading, flying over Eastern Europe, Turkey, and Saudi Arabia. It will continue in a south-southeasterly direction over the Indian Ocean. Following a short second burn of the RL-10C engine, Centaur will deliver the GPSIIF12 satellite to semi-synchronous orbit over the southern Indian Ocean, south of Australia. Separation will take place about 3 hours and 23 minutes after liftoff.